Our next speaker is Helmut Grießer from Adva Optical. Hi, Helmut, welcome.
Hi.
And he will speak about the deployment of QKD with commercial transport equipment. Helmut, the stage is yours.
Thank you very much for inviting me to give a talk at this workshop. I'm getting back a little bit more to quantum after this very interesting talks we heard just before in the last session. But as a disclaimer, I must say I'm not actually talking about entanglement-based quantum communication, but more about those things that are commercially available already, that prepare and measure quantum key distribution rather. But I want to show a little bit what the current status with respect to commercial or close to commercial products and components. And I think that will give also a little bit insight in what you would expect or what would be required if you actually want to go more into entanglement-based communication. The motivation for doing quantum key distribution, that's my motivation slide, is that actually it's not very difficult to tap optical fiber and to record the data you might find on this fiber. So what you can see on this slide is a bending coupler, which is maybe $100. And with such a bending coupler, you can tap fiber which has terabit of data on it. And actually, there are even commercially available devices which are optimized for recording huge amount of data. So they have this WDM receiver built in and big storage devices. So actually, it's not so difficult. And even if you might think hacking is easier than just tapping a fiber, it's essential to understand that there is really a huge amount of data which is traveling over those fiber, and that's the easiest way to tap huge amounts of data. And actually, we know that secret services have done that in the past and probably still do it. This gets me to the overview of my presentation. So I give a brief introduction how optical transport is secured today, and then we go into different transport system configurations for quantum key distribution. I will give a bit of an overview of QKD testbeds where ADFA was involved or still is involved, and I want to give an outlook. So for secure optical transport, so we see the data center setting where we have a connection between two data centers that needs to be secured, and the standard way, I would say, the standard classical way to do it is to use a symmetric encryption algorithm. So usually the AES 256, which is used to encrypt and decrypt the data in real time. That means those encryptors and decryptors can deal with 100 gigabit per second in real time, and or even 200 and 400 in the near future. And for the symmetric encryption key, there is an asymmetric algorithm involved that transfers the key over the unsecure public channel to both sides. And as we all know, with the advent of a quantum computer, practically all of those public key schemes which are used to exchange the key for the symmetric algorithm are vulnerable, and we need in the midterm at least we need to replace those public key algorithms by something different, and quantum key distribution is one way to do it. Just as a quick overview, obviously it's not just the key exchange itself which needs to be secured, or the encryption itself. what we need to make sure, in addition, for such a secure transport system, is the authenticity. That means we need to make sure that Alice is actually talking to Bob, and not to Eve, and Eve to Bob. So we would need to ensure authenticity to avoid a man-in-the-middle attack. This is actually also something you have to ensure for quantum key distribution. So that's not guaranteed by this the concept itself. And you would need to ensure data integrity. That means you would need to make sure that a potential attacker cannot change the data you're transmitting. And this is usually achieved by a special version of the AES 256, which makes changes then visible after transmission. Then if we talk about communication systems, you certainly heard about this OC layer system where you have different layers. Obviously, encryption can be also done at different layers, starting from the bit level physical layer over the data link layer, network layer, or transport layer. And for all of these layers, there are different versions of encryption protocols available. As a general concept, so the lower the layers, the easier it is to have a high throughput and to get high speeds. That's the reason why for 100 gigabit we encrypt on the physical layer, because you can achieve the higher speeds. Whereas if you go to a higher layer, the flexibility is increasing. You can get closer to the end device actually, but on the other hand, also complexity is increasing and throughput is lower. If we now have, as an example, the encryption on the physical layer, that's or on the bit layer, I should say, that's on optical transmission systems. That's the so-called OTN layer or optical OTH layer, where you do have the data positioned into frames with an header. And what you can see here is basically you have a dedicated bits in the header for doing the key exchange and for transmitting the authentication within the same frame. So that's a kind of in-band channel that ensures that you can do the key exchange for the public key algorithm, and you can transmit the authentication tag within the same data stream. You don't need an extra channel. So that's how it's done today. And now in the next step, we can look at how such a transport system configuration would look like for a quantum key distribution. For this, I would like to first distinguish between different notions you might get with quantum key distribution. So I called some use cases here. So certainly, what's discussed very often in terms of very high or kind of absolute security, what you can achieve with quantum key distribution, at least in principle, is a so-called information theoretic security that requires that you do a one-time padding for the encryption of your data. That means your data rate cannot be higher than the key rate you can get with the quantum key distribution systems. That means it's only suitable for low data rates. But as I said, it promises to provide the ultimate security. For very high data rates, we are looking at here for optical communication systems. You can use quantum key distribution to do the key exchange for the symmetric encryption. But obviously you don't get information theoretical security with such a scheme. So what we usually say, you get long-term security, long-term because you would expect that with such a scheme, you're no longer vulnerable to a quantum computer that can attack your public key scheme, and you would also not be vulnerable to additional mathematical discoveries with respect to new schemes for public key encryption, which people look at in terms of post-quantum encryption. So the hope is that if we assume that symmetric encryption stays safe, you wouldn't expect that you need to adapt or to change your public key encryption scheme or your key exchange for such a system. This is a case which is very interesting for the telecommunication use case we are looking at in the following. And now you might ask, okay, I already have the Diffie-Hellman for key exchange. I have QKD. I might use additional post-quantum encryption. So can I? Do I need to decide for any of those? And the good news is actually I don't necessarily need to decide. In principle, I can run all of these key exchange systems in parallel and combine them then into a secret key on both ends, same secret key on both ends to do the symmetric encryption. Whether it will be the case that in the future you will have all these three schemes in parallel, that's probably unlikely. But it's already clear that during the transition to to quantum safe encryption, people will use the classical key exchange and the post-quantum key exchange in parallel. And if you do have the requirements for doing quantum key distribution, it's definitely an interesting option to do quantum key distribution instead of post-quantum or even in addition to post-quantum encryption. So how does such a quantum key distribution look like? So what you can see here is on the principal setup as we can provide it already today. So you do have the classical data transmission, which you can show here. This is 10 gigabit transponder systems, which transmits the data 10 gigabit from left to right and 10 gigabit from right to left. So it's always both directions. And on the lower end, the big black boxes, these are quantum key distribution systems. It's a prepare and measure system where you do have also rack with a quantum key controller and the QKD transmitter and the QKD receiver. And we use an interface that transfers the key from the quantum key distribution to the encryptors. So the 10 gigabit encryptors are on the encryption card. And as I said, currently we can do up to 100 gigabit per second with encryption and a quantum key. So the quantum key is regularly renewed for every new session, obviously. So what you can also see here is that the quantum key distribution system, obviously you need a quantum channel, which ideally is a separate fiber, and in addition you need one or two auxiliary channels for the protocol, for the QKD protocol to work, and for some synchronization efforts. Yeah, so we had standardization before mentioned in a previous talk. So ETSI is actually a standardization institute that standardized the interface for the quantum key deliverable, and that gives us the possibility, if both companies stick to the same API, obviously we should be able to work with every company, every equipment that sticks to that interface. So now let's look a little bit more into detail about the DWDM configuration. Obviously, in order to reduce the number of fibers we actually would need. So what you can do in a wavelength multiplex systems, as those systems are usually set up, you can just use the system for the data transmission on additional wavelengths to transmit your auxiliary channels, and then you're basically left with one additional fiber you would need then for the quantum channel. In fact, if you have just two fibers available, there is also a possibility to have the quantum channel on the data on the same fiber as the data transmission, which obviously leads to some crosstalk onto the quantum channel, and you basically get a system where you would have to trade between the power you use for transmitting the data channels and the secure key rate you can get. We'll see that trade-off later on in one of the field trials. If you now, obviously we all know that the quantum key distribution systems, they have limited reach. And what you would need to do to extend that reach without having a quantum repeater available, and we all know that this is still some time out, you're running into the problems that you have to extend it. So this is done nowadays with so-called trusted node configurations, where you receive the quantum signal and you set up a QKD distribution link on the left side, and you set up one on the right side, and then you basically hand over the global key that you're using then for encrypting the actual data. As you can see here already, it can get pretty complicated with all these different filters you need in order to get the different signals multiplexed and demultiplexed. Okay, now we're going into those test beds. So the first test bed we were contributing to is a quantum communication hub QKD network in the UK. In Cambridge and close to Cambridge. So on the left side, you can see a metro ring that's built up with QKD equipment from Toshiba Research Lab in the UK. And you can see a trusted node link between Cambridge and the research facilities from BT in Ipswich. The distance for the link between Cambridge and Ipswich is 100 kilometers. But in order to be able to share the same fiber for the QKD channel in this case is working at 1300 nanometers, and you have higher attenuation for 1300 nanometers in the fiber, and they actually had to introduce 3 trusted nodes in order to bridge that distance. This slide shows again the configuration at transmitter, receiver, and trusted node side. So we have seen that already in one of the previous slides. So here a little bit on the data. As said, the quantum channel is 1310 nanometer. There are 5 100 gigabit channels running in the Z band, and you do have actually 3 auxiliary channels. 2 is for the QKD system, so 1 for the protocol, 1 for the key management, and 1 additional channel is so-called supervisory channel. That's actually the auxiliary channel for the WDM system. Obviously, if you optimize the system, you could probably save at least 1 or 2 of these auxiliary channels for an optimized integrated system. So now let's look at the measurements result that were published about. This is about the Cambridge Industrial Trusted Node Link. So what you can see on the right, these graphs, that's the yellow span between Ipswich and Burnham, I think, if I remember correctly. So you can see the 3 trusted nodes. And what you can see on the right side is the secure key rate versus the power for the classical C-band channels, so the 100 gigabit channels. And you can see that the higher the power you feed into the fiber, the lower actually your key rate gets. So as a background information, what we usually use for data transmission is so the standard launch power per channel is something like 0 dBm or maybe a little bit below, maybe -1, -2. Here you can see that you see already some degradation for this power. On the other hand, because the different spans are relatively short, so you can see here that the length is somewhere between 15, 25, 45, 36 kilometers. We actually can easily go in with less power because the 100 gigabit wavelengths are can go over much larger distances actually. So it's not really a problem to bridge the 100 kilometers with 100 gigabit wavelengths. You can see the same behavior then for the Q-bear. So if you increase the classical power, you get the crosstalk and the Q-bear is increasing. But still, you can say with such a setting, you can combine the quantum channel and the classical data channels without much loss in the secure key rate. So we can look at the Cambridge part, the metro ring basically that's supported by Toshiba. Here it's an aerial view and some results where they did long-term measurements for the key rate, where you could see that the key rate is pretty stable and they get also a quite high key rate, which is in the area of I think more than 100 megabit per second, but you have to say that actually the distances are relatively short within the metro area, and you have a similar trade-off here, more a bit into the more higher power with the optimum at 0 dBm, where you also can see an increase in the bit error rate. Here in this case, we had only two times 100 gigabit channels for data transmission on one of the links. Actually, we're doing more test beds now within the framework of the EU-funded Open QKD project, where one of the main goals is to set up and to test at different sites quantum key distribution for a large range of use cases in this case. So you can see there are a lot of carriers involved, a lot of service providers involved, which are really eager and interested to get their hands on those kind of equipment and to understand how well it works, what are the operational issues you might have. And so this is just a smaller part of the different use cases and test sites which are done within the project. But those are the ones we are currently supporting, but more are to come.
Helmut, we are in the question part of the.
Yeah.
So I don't know how many slides.
So yeah, I show my that's almost the last slide for an outlook. Now for the Open QKD program, it's really individual test beds. Now the question might come up: how does it work if we want to maybe a pan-European QKD network? And this is the outcome of a study where I looked into what does it mean if you take existing fiber infrastructure, or at least fiber infrastructure which is very similar to what you have in the real world, and would try to apply current QKD systems to it. And what you can see here on the left side is a graph with a distribution of the typical span lengths, and then you can see a graph of the network. And also red lines really means that you couldn't bridge them based on the current span length you have on those systems. So basically that would mean either you have to change the network, or you would really need to get better equipment, better QKD equipment. So what I assumed here is really a maximum loss budget of something like 22 dB, which is relatively typical to what you can get today. So as a motivation that it would be definitely would be beneficial if you want to use those kind of existing networks, existing fiber infrastructure to roll out QKD. And this is really the almost the last slide. I didn't really talk about entanglement assisted communications. Obviously, the missing building block now, if you want to get rid of these trusted nodes, which are a security issue, that's a quantum repeater, and here entanglement would come into play. There are also QKD variants that for example, device-independent variants that would employ entanglement. But obviously, what's available at the moment from commercial point of view is not entanglement based. I've seen one box which is probably not too commercial, where they employed entangled photons. But that's not the case. The focus from our point of view now, from the telecommunication point, is really not so much the entanglement assisted communication, but rather try to get size, cost down, and make it more compatible to existing data channels and the existing fiber network. Obviously, security certification is a very important point, and standardization. And with respect to standardization, I have one extra slide, which is kind of a little bit advertisement. And we had a discussion about standardization before in a previous talk. So there are different standardization organizations who work on quantum technology in general, or quantum communication more specifically on quantum key distribution. ITU is one of them. There is a focus group that works on quantum information technology for networks. And for a focus group, in contrast to the study groups, where they, for example, look into QKD networks, you don't have to be an ITU member. So basically everybody can join and contribute. Thank you.
Thanks, Helmut. I'll be quick. We have our two questions. So what do you think will be the first use case for entanglement assisted communication networks?
Yeah, I would say from my point of view on quantum key distribution, I would expect that it would be the quantum repeater. Yeah. Also, because at the moment I don't really know very interesting entanglement-based communication schemes for other types of communication, be it classical or quantum communication.
So what do you think is the main challenge, the main obstacle in the way to getting the repeater?
Yeah, what I put already here is the security certification and standardization. We have talked a lot about technical challenges. From my point of view, especially with respect to key distribution, I think that it is very important to standardize or better certify a certain security advantage you could get with quantum key distribution. I've mentioned post-quantum encryption before. If we don't manage to basically certify and define clearly what's the advantage of quantum key distribution, it will be very difficult to sell those kind of systems then to customers who are not into quantum communication really.